you all will be able to connect with me. I also thank Professor Vishnu and Dr. Rahul for giving me this opportunity to interact with you. So, without wasting much time, let us start. How much time, sir?
Madam, it is for 2 hours. As per your
Okay.
convenience, you can conduct me.
Okay, fine. Okay. Yes. I'll just share the screen and let me know whether my presentation is visible or not. Is it visible?
Yes, madam.
Yes, madam. Yes.
Okay, fine. So very good afternoon to again all the students, participants. I won't call them students because all they're doing PhD, so somewhere they probably are working as well as they are teachers. So today, as Vishnu sir said, I would be talking about the nuclear magnetic resonance spectroscopy. Before that, let us understand little bit what is spectroscopy. So since you are PhD students, most of you know about it, but still, I would like to just brush certain things and then move ahead. So, as the name indicates, spectroscopy means study of spectrum, study of spectra. But what kind of spectra? Spectra is nothing but in general, people call it as a graph. Now, graph can be generated by various ways. We can compare two or more things by using this graph. And when we talk about spectroscopy, we are talking about interaction of light with the matter. Whenever your electromagnetic spectrum, in general we call it as a light, when it interacts with the matter, it gives some, it has some impact on the matter. For example, just imagine that we are sitting right now, and wherever you are sitting, hope because it is a daytime, you can see a lot of things, you can visualize various things, you can recognize various colors. But if it is at night, you know that at night, if there is no electricity, there is no light, then we'll not be able to recognize these things. That means this light has something to do with the matter. And when you try to understand what is the impact of these radiations on matter, you'll find that your electromagnetic spectrum contains many kind of radiations. We can classify them on the basis of their energy or wavelength, and each radiation has different impact on the matter. Now matter can be anything like organic, inorganic, we know that, right? We can classify it as organic or inorganic. Now since today we'll be talking about organic compounds, organic matter, and its interaction with the light or electromagnetic spectrum. So if you see electromagnetic spectrum, you'll find that most of the times organic chemist uses radiations from UV visible region, infrared, and from radio waves, microwaves. These radiations are generally used by organic chemists. Now we do have other radiations, like we have cosmic rays, we have X-rays. These radiations also interact with the matter, but we generally do not use them to get information about, generally structural information about the earth. This is because if you see these radiations like X-rays and cosmic rays and gamma rays, they have got very high amount of energy, and our organic molecules are made up of these are covalent compounds. The energy what provided by these radiations will break these bonds, covalent bonds, which are weak bonds. There are two types of bonds, you know, that covalent and ionic. Most of the inorganic compounds are made up of ionic bonds, whereas organic compounds are made up of covalent bonds. So what you will find, the energy required to break this bond is comparatively is less. And if I provide these radiations, most of the times your compound will decompose because of breaking of bonds, because the amount of energy provided is very high. So obviously then we don't want to break bonds because we want information, mostly structural information of that organic molecule. That is our motto, to use this spectroscopic technique. So therefore, organic chemists generally do not use gamma rays, cosmic rays or X-rays. Now solid state X-ray sometimes is used for the finding some important information, structural information of organic molecule, but still very rarely they are used. So first condition, obviously your organic compound should be in solid state, then again it can withstand with the energy provided, then only we can use these X-rays to get the information. So we are normal small molecules, we do not use X-rays, but if you have a huge molecule like protein molecules, biomolecules, which are present in crystalline state or polymeric material, organic polymers, conducting polymers, then we can detect their structural information by using X-rays. But otherwise, we do not use these radiations. Then obviously, then you have UV visible radiations. Now the energy provided by these radiations is also high, but yes, still it can be used to get some information about that organic molecule. Now, what is that some information? So everyone knows that any molecule, if it is conjugated, means it contains more than two double bonds alternate with respect to each other, that is conjugated, then such kind of molecule will absorb radiations from UV visible region, and these electrons, pi electrons, will get excited from HOMO to LUMO, and you will get some spectra because of absorption of these radiations, and that spectra will help us to understand whether molecule is conjugated or not, how many bonds are in conjugation, and some other information like whether molecule is cis or trans. Such kind of information I can get if I use UV visible radiations. Now, all these spectroscopic techniques which we are going to use to find the structure are called as absorption spectroscopic technique. There are two types. One is absorption spectroscopy, and other is emission spectroscopy. Absorption spectroscopy is one where molecules will absorb some part of the radiations, and that those absorbed radiation will give some information about that molecule. Whereas in emission, what happens after absorption? That molecule, that bond undergoes some kind of excitation, and excited state is always an unstable state because it is a higher energy state. So it has to come back to original state or a ground state. In doing so, it will emit some of the radiations, and those radiations, if I study, that spectroscopic technique will be called as emission spectroscopy. Now, what we are talking is UV, IR, NMR, they all are absorption spectroscopic techniques. So, UV visible will give me information about the conjugation present in that molecule. If I use infrared radiations, then the energy provided by infrared is lesser than UV visible radiations. So, what it does to the molecule? What you will find that this energy which is provided by infrared region will not help any electron to go under excitation, but what it does, only the bonds can undergo excitation like vibrational excitation, rotational excitations, and those excitations also help to understand the bonding present in that molecule. Now, when we talk about organic molecules, we know that there are common things present in all organic molecules. What are the common things? Organic is nothing but carbon compounds. So obviously, carbon is present in that molecule, hydrogen is present in that molecule, and along with carbon and hydrogen, we have some other atoms like nitrogen, oxygen, sulfur, phosphorus, or halogens. These are the common atoms present in our organic molecules. So what you'll find that the moment you go to these other atoms, the type of bonding will change, and that type of bonding we can detect by using infrared radiation. So this infrared radiation or IR spectra will give us information about the type of bonding, or in other words, we generally call it that whether what kind of functional group is present in that molecule. Because The moment, if you talk about functional group, for example, if I say alcohol, there will be a bond between oxygen and hydrogen. So this bond will have different bond length, different bond strength, different vibrational rotational energies, and therefore its absorption will take place at different energy, and I will be able to distinguish between the OH and, let's say, I have C carbonyl group, okay, C double bond O, because two different atoms are connected, types of bonds are different, so I can distinguish between them. But if I have methanol, ethanol, propanol, a family of alcohols, won't be able to distinguish between methanol, ethanol, propanol, because all of them contain hydroxyl as a functional group. So these are the limitations then. So it will give only information about the some bonds present in that molecule, whether it is compound is aromatic, whether double bond is present, C double bond C or C double bond O. That information can be gathered by using. So UV limited to conjugated system, IR limited to only functional group, but I cannot distinguish various molecules from the same family by using infrared spectroscopy. So obviously we have some limitations in using these spectroscopic techniques. Then we have radio waves. Now their energy is still less than UV or infrared radiations. What if my molecule is exposed to these radio waves? What will happen to that? So what you'll find that if you talk about the structure of molecule, then you'll try to find out it contains molecule means made up of atoms. Then these atoms are various types of atoms. Again, we have carbon, hydrogen, as I told you, and other atoms. Their arrangement, and then you'll have different molecules as these atoms will be connected in different manner. So my NMR, that is radio waves, when fall onto the nucleus of any atom, again absorption is going to take place, and this absorption of energy will excite that atom and de-excite. Excitation because of absorption energy and de-excitation due to release of energy. In doing so, now this absorption and emission helps me to get some information about that molecule and what kind of information. So I'll be getting more of structural information by using this NMR. Now, there are various types of nuclei, like we have carbon, we have hydrogen, we have oxygen, we have nitrogen. So these all nuclei will are not having same properties because their atomic numbers are different. They contain different number of nucleons and electrons in a atom. So all these also have impact on their properties. What type of nucleons are present, as well as how many electrons are present around the nucleus of that atom, also have impact on their properties. So by using these properties, by understanding these properties, we can get
Ma'am?
the AMR spectra. Yeah, yes. Am I audible?
Yes, yes, yes.
Yeah. So, um, nuclear magnetic resonance spectroscopy, which in general we call it as NMR, is a non-destructive. All spectroscopic techniques are non-destructive techniques. Now, first thing, what do you mean by non-destructive? See, when you were at lower classes like first year, second year, third year BSc, if you're supposed to find out what type of compound is given, whether it is acid, base, phenol, what do? You go in a lab and try to find out its type. Okay, so you have various tests to perform. You take sodium bicarbonate, put it into your compound, and try to see whether effervescence are there. If effervescence are there, whether it is reprecipitated by adding some HCl, like that you do and find out what type of that compound is present. And then what do? You throw it in a basin. So your compound is lost because you have reacted, converted into something else. So such kind of technique to find its details is called as a destructive method. And spectroscopic techniques are non-destructive, means I can recover my compound back. So there is no loss of the compound, which is biggest advantage of using spectroscopic technique. What else are the advantages of using this technique? So the other advantage is that do you need very small amount of compound? You know that even if we give 3 gram, sometimes student will come and ask, I need more compound because my some of the test still I have to do. So human error is always there, and we do not measure and use randomly. We take the compound. So here we need very less amount of compound is required. That is another advantage, that it is non-destructive. Less amount of compound is needed, and obviously it is more authentic than, there is no human error involved in this technique, and obviously it is, hence it is more authentic. So obviously what information I'm going to gather is more authentic and more reliable than what we used to do in lab. Okay, so obviously it has got great importance. Is there any disadvantage? Yeah, disadvantage is there. What? So these instruments are very expensive. These techniques are expensive. Second thing, you need a means if once you get the spectra, you need a expert to analyze, to carry out, to take out the spectra. You need an expert. So these are some of the limitations of this, but these limitations one can overcome and get the spectra to get the exact information of that structural information about that molecule. So no doubt it is non-destructive, and it exploits the magnetic properties of certain nuclei. Now, this is another disadvantage we may call, that we cannot use this particular technique for all type of nuclei. We can use only for certain nuclei to study obviously their physical, chemical, biological properties. So what type of nuclei we can detect? That we'll see later on. But for the time being, just try to remember that all nuclei cannot be detected by using NMR. So this is one of the another disadvantage of NMR. In 1937, Rabi was a physicist who actually predicted NMR, and he got Nobel Prize for this in 1944, where what he did, that he could, by using these radiations, um, he observed a atomic spectra, and then later on, with various other inventions, we have developed a instrument which will provide us the spectra in the readable format, and which will give information about the structural information about the molecule. So just now we spoke that we have applications, lot of applications for using this NMR spectroscopy, and that is why obviously we are supposed to study this. So today, any you take zoologies, you take botanies, you take biotechnologies, you take the food uh, food scientist, or your any person you take, if you're uh, try to find out the information about any matter, first comes is a NMR. So obviously it has got a lot of applications, and that's why we try to understand what is it about. And for various things, like as I told you, that no doubt only structured information, but stereochemistry, to check the purity and other things, we can use this NMR spectroscopy. So let us try to understand first the principle of NMR spectroscopy. Yes. Okay. So as I told you, that it is based on the fact that all nuclei are electrically charged. We know that what is nucleus? So nucleus has nucleons, that it contains protons and neutrons, right? Neutrons are electrically neutral, but protons are positively charged. Everyone knows about this. And these, any charged species, whenever it spins, it moves, it generates its own magnetic field. Okay, so we know that nucleons are also moving, nucleus is also moving, and nucleus is surrounded by electrons, they are also moving. Okay, so all electrons are charged species, nucleus is charged species, and because they are moving, they are spinning, they generate their own magnetic field. Now, such kind of nuclei, if I put into external magnetic field, Now, from where this external magnetic field will come? Obviously, from your instrument. Your instrument will have its own magnetic field, and your nuclei or your atom or your molecule has atoms which also have its own magnetic field. So there will be interaction between the external magnetic field and the magnetic field generated by your atom. What happens when you keep your atom or your molecule in the external magnetic field? So the energy is transferred from external magnetic field to the atom, and since whenever it is provided as per its magnetic field, the energy is provided as per its atom's magnetic field, it will absorb radiations and it will get excited from ground state to excited state. The moment it goes from ground state to excited state, obviously it goes from stable to unstable state because it has got extra energy. And so the life at the excited state is very less because it is unstable. It will come back to its ground state, but in doing so, now it will give out, it will emit the radiation which it has taken from the external magnet. Obviously, as I told you, nuclear magnetic resonance makes the use of radio waves. So the energy provided, energy emitted will also be in the region of radio waves. So this excitation and de-excitation of your atom will give you some spectra, and that spectra we will call it as a NMR spectra, which will help us to get information about that particular molecule. So this is the basic principle of your NMR spectroscopy. So as I told you that let's say this is your these are the atoms with their own nuclear spins moving, spinning in random direction. The moment I put in external magnetic field, this B0 indicates the external magnetic field, or it is also called as applied magnetic field. As we know that there are various instruments like 60 megahertz, 120 megahertz, 300, 500, 800 megahertz. We have a lot of instruments with these megahertz indicate their power. Okay, higher the applied magnetic field of that particular instrument, higher will be the power of that particular instrument, which will help to understand more complexity of that particular molecule. No doubt all will give same information, but the information provided by high strong magnetic field will always be a better information than 60 megahertz instrument. So what you'll find that these nuclear spins which are in random direction when they are not in the external magnetic field, the moment they are in the external magnetic field, they were either aligned in the same direction of applied magnetic field or in the opposite direction of the applied magnetic field. Those which are in the opposite direction, obviously they have absorbed energy and gone to the excited state, and some of them are in the ground state. So this is how first when you put your molecule into applied magnetic field, their spins, their own spins will interact with the external magnetic field. And how do you understand? So the spin state will be either in the same direction or in the opposite direction of the applied magnetic field. This is the common, we can say, the NMR spectrophotometer has these are the things which are required in the spectrophotometer. As I told you, it has obviously magnet because what you need is the external magnetic field. Then you have a cuvette which is placed in between this external magnetic field. This cuvette is nothing but your test tube like thing, a cell, glass cell, which contains your compound dissolved in some solvent. Most of the times we have to dissolve our organic compound in some solvent, and generally what we use is a deuterated solvent. Now why deuterated solvent? So what you'll find, an instrument which detects hydrogen will not detect deuterium. Okay, just um, a layman will understand this language. In that language, I am saying that we generally use deuterated solvent like CdCl3 or DMSO, depending upon polarity of your compound and polarity of the solvent. We know like dissolve like simple principle is there, and on the basis of that, we'll decide what solvent to be used for getting NMR. Now, I can use acetone, I can use ethanol, but then problem is acetone, ethanol, they themselves also absorb in, they will also have their own peaks in the spectra, and they probably will interfere in the analysis of unknown or your molecule. That is why we use deuterated solvents. So we dissolve them, and along with that, what we need is a internal standard. Now, what is the internal standard? So whenever we take the spectra, we generally use TMS, that is tetramethylsilane, as an internal standard to find out the NMR spectra, whether it is H1 NMR or CMR. Now, this tetramethylsilane is like an alkane, and most of the organic compounds are soluble in this compound. So, probably sometimes you don't have to use solvent also if you are using TMS. It is also soluble in most of the organic solvents. So, if you are using solvent, TMS will also be dissolved in that. And the if you imagine tetramethylsilane, it is like your tertiary butane, or neopentane rather. And what you'll find that all the methyls are highly shielded. I'm using this word, but later on we will talk about what is shielded and deshielded. What you'll find that TMS peak is most of the times comes first, and then all other protons of your organic molecule will appear. So it is very easy to detect peak of TMS. So these are the properties of tetramethylsilane can be used to make its use as an internal standard. So we have a cuvette with your organic compound and TMS dissolved in it along with some solvent. Obviously, this is detected. It is connected to the detector, and obviously, detector will be connected to the printer. It is like your computer, which you can see on a monitor also what type of spectra you are getting, and obviously you can take the print of that. So this is general structure of your NMR spectrophotometer. This is how it look like internally. Yeah. So, as I told you, that NMR spectroscopy works by placing sample in a strong magnetic field. Just now we have seen how it looks like and where the magnetic field is, and bombarding it with a radio waves. As I told you, that we are going to use radio waves to detect the NMR of certain atomic nuclei. Now, again, we are saying not all type of atomic nuclei, but certain atomic nuclei. What kind of? We will talk about it immediately. So what happens with these nuclei who are spinning? They absorb some energy and they change their spin state, as I told you, from ground to excited state, and that change in spin state will help you to what type of radio waves are absorbed, and that will help to get the spectra of that particular molecule. Okay, now what you'll find that we can categorize atomic nuclei into various categories. For example, we can have atoms uh, which have even mass number, that is containing even number of protons and neutrons, that is they contain even number of nucleons. If I take such kind of atom, like for example, let's take carbon. You know that carbon atomic mass number is 12. Its 12 atomic mass number indicates that it contains 6 protons and 6 neutrons. Okay, 6 protons, 6 neutrons, total 12 number of nucleons present. That is even number of protons and even number of neutrons. You'll find that its spin quantum number is 0. That means it will not show any change in its spin state when I put it to in the NMR spectrometer, photometer. If it is not changing its spin, it will not give any spectra. If it is not giving spectra, I will not get any information about that particular atom present in that molecule. So this is a disadvantage that I cannot detect C12 by using my NMR spectra. Along with that, we know that oxygen, whose atomic number is 8, atomic mass number is 16. 16 indicate again 8 protons, 8 neutrons, even number of protons, even number of neutrons. I value, that is spin quantum number is 0. No change in spin will take place when it is put into NMR spectrophotometer. And if it not going to absorb any radiations, it will not generate any spectra. So such kind of nuclear whose spin quantum number is 0 are NMR inactive nuclei. So as we had discussed that certain nuclei can be detected. So why certain? So what is the condition which nuclei cannot be detected? Carbon, oxygen, sulfur, and many other. But we are talking about these three because our organic compounds contain most of the organic compounds contain carbon, oxygen, and sulfur. Now, but still we have a CMR. But if you remember, CMR, we do not write just CMR, we write 13 above that. Okay, superscript 13 is always written. Why 13? So carbon exists in isotopic form like C12, C13, and C14. C14 is also inactive. C12 is also inactive. C13 has odd number of nucleons, and that is why its I value, spin quantum number value is 1 by 2 more than 0 becomes NMR active nuclei, and therefore we can detect C13. So C12 we cannot detect, O16 we cannot detect, sulfur we cannot detect because they have 0 spin quantum number. They are called as NMR inactive nuclei. So we can categorize our particles into two as bosons and fermions. Now what are bosons and what are fermions? So all those nuclei which will spin, which will have spin quantum number greater than 0 will be classified as bosons and fermions. Now what are bosons? All those nuclei whose mass number is even and contain odd number of protons and odd number of neutrons. When two odd things are added, it becomes even. You know that, right? So nuclei can be classified. Now these are NMR active nuclei which can be classified as bosons and fermions on the basis of what are the whether their proton nucleons are odd number or even number. So what you will find, bosons, for example, deuterium, if I take deuterium, has one proton and one neutron. So one proton and one neutron, odd number of proton, odd number of neutron, but mass number is 2, even mass nuclei. So such kind of nuclei will be called as bosons, can be detected in NMR. It is called as NMR active. Now what is fermion? So it is odd mass nuclei which contain odd number of nucleons, and that is why it will have always a spin quantum number in fraction like half, 3 by 2, 5 by 2, something like that, and it can be detected. As bosons, they will have integral spins like 1, 2, 3, not 0, but 1, 2, 3, and hence they can be detected. So I value for bosons will be an integer 1, 2, something like that. But for fermions, it will be always in fraction, that is either half, 3 by 2, 5 by 3, something like that. So what is the difference between bosons and fermions? Bosons have odd number of protons, odd number of neutrons, but mass number is even. Whereas fermions have also odd number of nucleons, but both are not odd. One is odd, other is even, and that is why mass number becomes odd number. Both these bosons and fermions have I value, that is magnetic spin quantum number is greater than 0, and that is why they are called as NMR active nuclei because they can be detected in NMR. Okay, so our hydrogen whose atomic number is 1, atomic mass number is 1. So it's odd number nuclei, mass number nuclei with odd number of nucleons. So it is called as fermion. But if you take deuterium, its isotope, it is boson because it contains odd number of protons, odd number of neutrons, but its atomic mass number is even. So we can classify NMR active nuclei as bosons and fermions. So hope you understand what's the difference between bosons and fermions and how are they classified. Both are NMR active nuclei. So one thing is there now, we understand what kind of nuclei we can detect and what kind of nuclei we cannot detect by using NMR. So all those nuclei whose spin quantum number is 0, all those nuclei which contain even number of protons and neutrons cannot be detected by using NMR spectroscopy or NMR spectrophotometer cannot detect this nuclei. But bosons and fermions, that is even mass nuclei or odd mass nuclei containing odd number of protons, neutrons, or nucleons can be detected by using this NMR. So this is very basic. We should be able to understand what I can detect, what I can't detect by using this particular technique. So obviously now first we will be talking about hydrogen magnetic resonance, because you know all organic compound contain carbon and hydrogen. So obviously we are going to use this technique to detect carbon and hydrogen first. No doubt we also have nitrogen magnetic resonance, we also have phosphorus magnetic resonance, we also have fluorine magnetic resonance. These all techniques are there. But as you know that there are very few nuclei, very few molecules contain these atoms. But all organic compounds, all biomolecules contain carbon and hydrogen. So obviously the information provided by H1 NMR and C13 NMR will be much useful as compared to the other NMR techniques. Okay, but if you have a biomolecule, if you have a polymeric molecule, they contain lot number of nitrogens, and along with that they also have fluorine and phosphorus. So obviously there, along with H1 NMR, C13 NMR, we use these other make use of these nuclei also to find out the NMR spectrum. But today we are not talking about those. We'll be talking about exclusively PMR spectroscopy. So PMR is proton magnetic resonance, which is also called as H1 NMR. Now, why do we call H1 NMR as PMR? We will never call CMR as PMR, okay? Only H1 NMR will be called as PMR or proton magnetic resonance. Why? So again, try to understand, try to imagine hydrogen atom. Hydrogen atom has a nucleus which contain only one proton. It does not contain any neutron. This is the only element in periodic table which do not contain neutron in it. And it has one electron which is revolving around its nucleus. So what you'll find that H1 nucleus, if I take, now I'm not talking about extra nuclear part, okay? I'm talking about nucleus because we are talking about NMR means nuclear magnetic resonance. We are talking about it's a property of nucleus. So hydrogen is the only nucleus whose nucleus is nothing but a proton. Okay, so because its nucleus contains only one proton and there is no neutron present in hydrogen, that is why we call H1 NMR as PMR, that is proton magnetic resonance. Now, when I take this hydrogen, obviously hydrogen is not present in elemental form. It is bonded with something else. It is bonded with carbon, it is bonded with nitrogen, it is bonded with oxygen, it is bonded with halogen or something else, okay? So what you'll find that the presence of this electron present in the around the hydrogen atom, this electron sometimes is close to hydrogen or going away from hydrogen. It depends upon what? It depends upon the environment around this hydrogen nucleus. Environment means what? So what type of bond this hydrogen has formed? With which other atom it has formed the bond will decide whether electron is going close to the nucleus or going away from the nucleus. If his electron is going close to nucleus, we say that nucleus is shielded, and if it is going away from nucleus, we say that the nucleus is de-shielded. Shield means what? You know, um, when Raja Maharaja used to go for war, they used to have a shield and sword, okay, with them. So the shield is helping them to protect themselves, right? Same way, your nucleus is there and electrons are coming close to the nucleus, then we say the shielding, and when electrons are going away from the nucleus, we say they are undergoing de-shielding. nucleus is reshaped. How does it affect the property of that hydrogen, or how does it matter in NMR? It matters a lot. So your magnetic field or the resonance of that particular hydrogen from lower to higher state, which is going to take place when it is placed in the external magnetic field, will be decided by the other atoms which are connected to it. Okay. So what you'll find, for example, there are two molecules written over here. One is methyl chloride, another is methane. Okay, what is the difference between these protons? There is difference. All four hydrogen atoms over here in methane are equivalent in all respect. All three hydrogen atoms in methyl chloride are also equivalent in all respect, but there is difference. What is the difference? Now, a carbon to which these hydrogen are attached is attached to Cl. Here, we don't have such kind of situation. So what you'll find that Cl is more electronegative than hydrogen or carbon. So what it does, it try to take electron from carbon because it is directly bonded to carbon. What it does, we call this as um, the electronegativity of Cl is greater, that way it will pull electrons toward itself. In doing so, what happens? Carbon start giving electron to Cl. The moment carbon starts giving electron to Cl, carbon start acquiring positive charge. You know what is electronegativity. What happens? A covalent bond becomes a polar covalent bond if you have a electronegativity difference. The one which is more electronegative will acquire partial negative, and the one which is electropositive will have partial positive charge. We call this as the inductive effect. Minus I effect of Cl will create partial positive charge on carbon. Now what happens? Then carbon starts taking electron from hydrogen, and in doing so, what happens? The hydrogen atoms in methyl chloride will be called as more de-shielded than in methane, because the electrons from hydrogen are taken by this carbon which is attached to Cl. So hydrogens of methyl chloride are more de-shielded as compared to CH4. So the electron density is lower in methyl chloride hydrogen. We are talking about hydrogen nucleus. The electron density will be less around the nucleus in methyl chloride as compared to in methane. Similarly, if I take now another molecule, let's say I take chloroform. There is difference between CH3Cl and CHCl3. What's the difference? Again, there is only one proton, whereas here three protons. This carbon is attached to three Cl atoms. Here, the carbon was attached only to one Cl atom. More the number of electron withdrawing group, more will be the polarity, more will be the de-shielding effect, and the proton of CHCl3 will have very less electron density around it as compared to CH3Cl proton. And we can distinguish then between a proton of CHCl3, proton of CH3Cl, and proton of methane. Why? Because in all these molecules, the electron density around the hydrogen is different. Because electron density is different, they will resonate at different magnetic field, and because they require different energy, different electromagnetic field for their resonance, we can distinguish between these various protons present in that organic molecule. If I take CH4 and you say that all four hydrogen, can we distinguish between them? No, we can't, because all these protons have same environment. All these protons are attached to same carbon, and then they will have same electron density around them. The nucleus of these hydrogen atom is surrounded, their surrounding is same. That is why the resonance energy will also be same. Their absorption energy, the applied field, whichever applied field they absorb will be same. So I cannot distinguish between four protons of methane. I'll not be able to distinguish these three protons present in CH3Cl. But yes, I can distinguish between CH4 and CH3Cl. I can distinguish between CH3Cl and CHCl3, because electron density around this proton is not same, it is different. Who decides this? Not hydrogen. This is not decided by hydrogen. This is decided by the environment around the hydrogen. Which atoms are attached to this hydrogen? That those elements, those atoms will have impact on the electron density of hydrogen, and in if the electron density is increased, we say the proton is shielded. If the electron density is decreased, we say proton is de-shielded. And because there is shielding and de-shielding, we can distinguish between various types of proton present in our organic molecules. That's a great thing, because otherwise, if I can't distinguish between CH4 and CH3, this technique will be useless for us. But because these impacts are there, because the surrounding is affecting the electron density around the hydrogen, I can distinguish between these various protons, and we can understand what are the different types of hydrogen present in given organic molecule. So this is one of the best thing, best information we can gather by using NMR. So when I take NMR spectra, I know that my organic molecule, I have to dissolve, keep in an external magnetic field, and run the instrument and get the spectra. Now what I'm going to look at, what information I'm going to get by using this H1 NMR. So there are various information depending upon various things. For example, we look for most of the times four important things. One, how many types of hydrogens are present? Then, where are the peaks located? Three, what is the intensity of the peak? And three, what is the splitting pattern of the peak? This will give me a lot of information about the proton, surrounding of the proton, and then obviously bonding and the structure of the molecule. So we are going to look at these four things uh, when we talk about the NMR spectrum. So first thing I'll see, how many signals are there? How many peaks are there? So peak, signal, one and the same. Okay. So how many peaks or signals are there? That will tell me how many types of hydrogen present. For example, again we take these three molecules. If I take CH3Cl, if I take CH4, if I take CHCl3, I get only one peak for all these molecules. Why? Because all protons in CH3Cl are equivalent. All four hydrogen of methane are equivalent. And there is only one hydrogen in CH3Cl. So I'll get only one peak for all these three molecules. Then we look for the position of the signal. That means we talk about the chemical shift, the scale which utilized to get the position of signal is called as chemical shift and denoted as delta, and ppm is the generally unit used for chemical shift. Acid there is no unit, but ppm is parts per million in this unit we measure. So it will help me to understand that what type of hydrogen is present, means what we'll talk later on. And then each peak height is may be same, may not be same. This height of the peak, we call it as the integration, or it is also called as area under the peak, area under the signal, will help me to get the information about how many types of hydrogen and how many hydrogens of each type are present in that organic molecule. And then splitting. Now, what is splitting? Later on we'll talk about. But these are the four things we will look at to get the information from NMR spectra. So this is how the NMR spectra will look like. And as I told you that number of peaks means over here there is only one, but 2, 3, 4, 8, 10, whatever number we will count it. Then this is the scale called as a chemical shift. We generally expressed in parts per million, that is ppm. Now generally in the scale in PMR or H1NMR is 0 to 12, sometimes goes to 15, not more than that. So the scale is very less, only 0 to 12, maximum 15. So one of the disadvantage of H1NMR that sometimes, if you have many types of hydrogen present, then there is clustering of the peaks takes place, and then it becomes very difficult to understand what type of protons are, or what is the chemical shift, or what is the splitting pattern of that proton. But if I change the instrument If I increase the operating frequency of the instrument, I can simplify the spectra, and there are certain more things which can be done. If you have a complicated molecule, we can simplify spectra by various other ways that we'll see later on. For the timing, this is how the spectra will look like. The height of the peak, the area under the peak will help me to get the information about how many hydrogen atoms are present of same type. The number of peaks will tell me what are the different types of hydrogen present, and chemical shift will help me to get some information about that molecule. Now, what information? So we'll see what information. But so number of signals, number of peaks, all magnetically equivalent nuclei will have same peak. For example, just now we spoke methane, ethane. If I take these two molecules, this contains 4 hydrogen, this contains 6 hydrogen, but I'll see only one peak because they all are equivalent in all respects. As I told you, what do you mean by equivalent? The electron density around these hydrogen atoms will be same, therefore they will resonate at the same frequency, and that is why we cannot distinguish between them. So number of signals depend upon the type of hydrogen atom present in that molecule. For example, if I take this molecule, what is this molecule? What do you call this molecule? Are you there with me? Can you unmute and answer? Yes? Yeah, it's a cyclohexane. Very good. The cyclohexane, you know that it does not exist in this form which I have written. How does it exist? You can unmute and speak also. There is no problem. Yeah? Anyone? Cyclohexane exists in chair form, boat form, then twisted boat. Lot of forms are there, right? Cyclohexane. But most stable form is chair form. So Satyam has written that it exists in chair form. So we take this answer. Okay. Now in chair form, there are two types of CH bonds. Can you tell me what are the two types of CH bonds or two types of hydrogens are present in that molecule? Yes? Anyone? When I draw cyclohexane, hydrogens are of two types. Some of the hydrogens are perpendicular to the plane and some of them are going in the peripheral side. So those which are perpendicular are axial and those which are peripheral are equatorial. Very good. So Satyam again has answered. It is axial and equatorial. Now you know that this chair also has another thing, that it keeps on flipping from one chair to other chair. When it flips, what happens? Axial becomes equatorial and equatorial becomes axial. In cyclohexane, there are 6 axial and 6 equatorial hydrogen atoms are there. But what happens? Since at room temperature the energy provided is the energy required for this flipping is so less that we cannot distinguish between axial and equatorial, because every time flipping is taking place, axial becomes equatorial and equatorial becomes axial. Then, if I take the spectra of cyclohexane, you'll find that there is only one peak equivalent to 12 hydrogen atoms. I cannot distinguish between axial and equatorial at room temperature. There is one technique by which we can distinguish. If I take this spectra at a very low temperature, at liquid nitrogen temperature, then what you will find that it exists. We can lock the flipping of the chair, and at that time we will be able to distinguish between axial and equatorial. At that time it will show me 2 peaks in my H1, H1 NMR. But otherwise at normal room temperature it will give me only 1 peak. The next molecule very looks like the previous one but totally different. It is benzene. So what you'll find, benzene, all hydrogen atoms are equivalent in all respect. If I carry out, let's say, substitution reaction for benzene, what is substitution? You're going to replace one of the hydrogen by some other atom or group of atoms. Now, if I carry out this reaction, you know that I can replace any hydrogen. We cannot distinguish between various hydrogen atoms. And since I can replace any hydrogen atom, such kind of protons will be called as chemically equivalent nuclei. And this chemical equivalent nuclei, hydrogen atoms, we cannot distinguish by using PMR, and therefore all hydrogen will appear as a single peak. We'll see only one peak for benzene. Then we have another molecule. Here also you can see now there are total 12 hydrogen atoms like your cyclohexane, but all hydrogen atoms are equivalent in all respect. All are attached to a sp3 carbon, which is attached to a sp2 carbon. All of them will have same electron density around them. Therefore, we cannot distinguish between them. They will appear as a single peak. We take another molecule now. Again, here we have 9 hydrogen atoms, but all of them are equivalent. We cannot distinguish between them. They will appear as a single peak. Now I got another simple molecule, that is ethyl bromide. What you'll find now, this is CH3, this is CH2. There is difference, right? And this carbon is beta with respect to Br, CH3 is beta with respect to Br, whereas CH2 is alpha with respect to Br. So obviously their environment is not same, therefore they will not appear as a single peak, but I can distinguish between CH2 and CH3. So what you will see, that there will be two peaks for this molecule in PMR, because we have two different types of hydrogen atoms. One type is CH3, another type is CH2. So two different types of protons are there. Therefore, I'll see two peaks in PMR for this molecule. I have another molecule where we have CH3, then CH, and then again CH3. What you'll find, that CH3, this one and this one, equivalent in all respect, same environment chemically, chemical environment is same, and therefore we cannot distinguish between them by using PMR. I'll see again two peaks, one peak equivalent to this 6 hydrogen atoms, and other peak equivalent to this 1 hydrogen. So we'll have two peaks in PMR. So number of peaks are decided by the chemical environment of that particular proton. We have another molecule. We have protons attached to aromatic ring. There are 4 protons attached to aromatic ring, and we have these CH3s. Okay, there are 2 CH3s and aromatic protons. I cannot distinguish between these 4 hydrogen atoms of aromatic ring. I cannot distinguish between these 6 hydrogen atoms. So again, I will see two peaks for this particular molecule. One for these hydrogen which are attached to sp3 carbon, and other protons which are attached to aromatic rings. So again, I'll see two peaks. Let's take this molecule now. What do you find? That we have aromatic proton, we have aliphatic protons. In aliphatic also we have CH3, we have CH2. So I can obviously distinguish between this CH3 and this CH2, and I can always distinguish between these various protons present in aromatic ring also. Because if I take hydrogen attached to this particular carbon, I'll find that this hydrogen is ortho with respect to CH3. It is meta with respect to CH2. So its environment and environment of this proton is same. So these two protons will appear as the same peak. Whereas these two protons, which is meta with respect to CH3, and this is para with respect to CH3, we will be able to distinguish by using PMR. But these two proton will also will not be able to will be able to distinguish, because this hydrogen is ortho with respect to CH3. This is meta with respect to CH3. So all 4 hydrogen atoms have different chemical environment. Therefore, I will be able to distinguish between all these 4 protons. Okay, so this is how we find out how many number of peaks or number of signals are present in that organic molecule. This is the first information we are going to look at. Okay, and that is decided by the chemical environment of that particular proton. So if I take propyl bromide and propyl bromide, 1, 2, and 3 peaks will be seen. I can distinguish between this CH2 and this CH2. Why? Because this CH2 is beta with respect to Br, alpha with respect to CH3. This CH2 is alpha with respect to Br and is beta with respect to the CH3. So the chemical environment of this CH2 and this CH2 is not same. So obviously we'll be able to distinguish between these CH2s also. So 1, 2, and 3 three peaks will be seen for this molecule. Take this molecule, CH3 and CH3. Even though both are CH3, they are not same. They are not equivalent. The chemical environment is not same. You can always check their relation with the other atoms. Okay, this CH3 is attached to CH. This CH3 is attached to CH2. Is it same? No, it's not. So obviously I will be able to distinguish between these two CH3s, and obviously the other is CH and CH2. So I'll see four peaks in PMR for this particular molecule. If I take this molecule, we have three CH2s over here. Okay, I can distinguish this CH, the middle one, from these two. Because their environment, again we have to check the environment. This CH2 is attached to Cl, alpha with respect to Cl. This CH2 is beta with respect to Cl. This CH2 is beta with respect to Cl. But these two CH2s, which are directly attached to Cl, we will not be able to distinguish between them because their chemical environment is same. We cannot distinguish between them. So even though there are three CH2s, we'll see only two peaks. One for this CH2 directly attached to Cl and other for the middle CH2. So this is how first thing we are going to look at is the number of peaks present in that PMR. What is the second thing I am going to see? I'll see the position, that is the chemical shift of that particular proton. How does it help me? It helps me a lot. That tells you what can be the structure of that molecule. It is very important information which we are going to have, that is chemical shift. Now, those protons whose chemical shift is less are said to be upfilled protons, and whose chemical shift is high are called as downfilled proton. Okay, this is the language of spectroscopy, NMR spectroscopy. Upfilled, downfilled. Upfilled means delta value is less, or we say it is a shielding zone, and downfilled means it is called as a de-shielding. What is shielding? What is de-shielding? When we say shielding, we are talking about electron density going close to the nucleus of hydrogen. When we say de-shielding, electron density is going away from the nucleus. Please remember this. Very simple. Shielding means electron going close to the hydrogen nucleus, and de-shielding means electrons are going away from the nucleus of the hydrogen atom. Now, we have various types of hydrogen in what? This hydrogen can be attached, now generally they are attached to carbon or oxygen, nitrogen, sulfur. Okay. Now, carbon we have different types. We can classify carbon on the basis of hybridization as sp3, sp2 and sp type of carbon. Okay. As the hybridization changes, the property of carbon also changes. You know that, right? Among sp3, sp2 and sp, can you tell me which is having more electronegativity or which is more electron withdrawing among these three? Can you answer this? We have sp3, we have sp2 and we have sp type of hybridization. A carbon with different hybridization has different electron withdrawing capacity. It depends upon percentage of S character. In sp3, percentage of S character is 25%. In sp2, it is 33%. And in sp it is 50%. More the percentage of S character, more is the electron withdrawing capacity. As rightly said by Satyam, that sp carbon is having more electron withdrawing capacity as compared to sp2 and sp. Percentage of S character directly proportional to its electron withdrawing capacity. One thing. So obviously, if hydrogen is attached to sp3 carbon, if hydrogen is attached to sp2 carbon, or whether it is attached to sp carbon, they will not have same electron density around them, and because their electron density will be different, we can be able to distinguish between sp3, sp2 and sp type of carbon atom. First thing we will always remember that the moment type of hybridization changes, its chemical shift will also change because property of that carbon changes. Then let's say in sp3 carbon, we can have primary, secondary and tertiary carbon. Primary carbon will be the most shielded proton. For example, your methane, for example, your ethane, all CH3s and CH2s are primary carbon atom. Their chemical shift will be minimum. Then comes secondary, that is CH. Okay, sorry, secondary is CH2, and then comes tertiary as CH. So CH has more substituents, more the number of substituents around it, more will be the de-shielding effect, or what we'll say the delta value will increase. So in among sp3 also, I can distinguish between primary, secondary and tertiary carbon, hydrogen attached to this carbon on the basis of their chemical shift. Then comes now sp2. Again, sp2 can be of two types, we can have olefinic carbon and we can have aromatic carbon. Olefinic carbon comparatively will have less delta value as compared to aromatic carbon. But all sp2 carbon will be more de-shielded as compared to sp3 carbon. So the range of sp2 carbon, hydrogen attached to sp2 carbon, starts from 4.5, 4.6 to it might go up to 8.7, 8.8, 8.9, depending upon chemical environment of that particular proton. How it changes later on, we'll see with some example. For the timing, the range is that high. Please remember that. And then comes your sp. Now, question will arise that even though the electronegativity, electron withdrawing capacity of sp carbon is greater than sp2 or sp3, still the delta value of sp hydrogen atom attached to sp carbon is in between sp3 and sp2. Highly de-shielded are sp2, aromatic protons are highly de-shielded, then your olefinic, then comes your alkyne protons, and then comes your alkane protons. Now, why it is so? So this is not the only factor, obviously. There are some other factors which decide. On the basis of that, you'll find that even though electronegativity of sp carbon is greater, the delta value of hydrogen attached to sp carbon is less as compared to the delta value of hydrogen which is attached to sp2 carbon. Why? We'll see. We'll talk about it later on. Because we have just now spoken only one factor, that is electron density on the basis of type of hybridization of carbon. Then, along with that, if some halogen is present, oxygen is present, alcohol, ether, ester, amine, everywhere you'll find that the electron density will be different and therefore chemical shift will be different, and such protons then will be classified as shielded, de-shielded, something like that. Okay. Let's take one example. Just now we spoke CHCl3, CH2Cl2, and CH3Cl. These are the three hydrogen molecules where all hydrogen atoms are sp3 carbon. But still the chemical shift, if you see, in CH3Cl, proton appear at 3.05, in CH2Cl2, proton appear at 5.3, and in CHCl3, it appears at 7.27 going in aromatic region, even though it is attached to sp3 carbon. So, why is this happening? This is because, as I told you, that it is not about only carbon which is directly attached to hydrogen, but along with that, what other atoms are present in that molecule? Here, there is one chlorine. Here, there are two chlorine atoms. And here, we have three chlorine atoms. Because now you know that as the number of Cl are increasing, what you'll find that electron withdrawing capacity of Cl is greater than hydrogen. What we are doing every time, replacing hydrogen by Cl. So because of that, electron withdrawing capacity of two chlorine atom is greater, and then 3Cl, it is much higher. Because of that, hydrogen is affected. Electron density around hydrogen is affected, and we will say that this particular proton in CHCl3 is the most de-shielded proton because of the electron withdrawing effect of 3Cl atom. We are talking about inductive effect, that is electron withdrawing effect. Inductive, we can have two types. One is electron donating, other is electron withdrawing. Plus I, minus I. Minus I means you have some electron withdrawing group, plus I means some electron donating group is present in that. If you have plus I effect, hydrogen will become shielded because electron density will go towards hydrogen. Your nucleus will be shielded with electrons, and we will say that such kind of proton is shielded or its delta value will be less. But the moment you replace electron donating by electron withdrawing, like Cl over here, what you'll find that electron density will go away from the hydrogen nucleus, and we call that particular proton is de-shielded. How do you understand it? From its chemical shift, from its delta value. Higher the delta value, more is the de-shielding effect. So it's one of the best example to understand how your electron density is connected to the chemical shift of that proton. Higher the value, more is the de-shielding effect. Lesser the value, less is the de-shielding effect or a shielded proton, we can say. So among these three, this proton is shielded, de-shielded, highly de-shielded. Now understand the language. Shielded, de-shielded, highly de-shielded when I'm comparing this thing. But if I take CH3Cl and if I take methane, I'll say this is highly de-shielded because I'm comparing with what? Methane. So it is comparative, relative. We are talking about uh, comparative chemical shift of proton with respect to these three molecules, highly de-shielded, and this will be shielded among these three. Now here another molecule is there, there are various CH2s present in these molecules. So one CH2 is gamma with respect to Br, this CH2 is beta with respect to Br, and this CH2 is directly attached to Br with alpha. So first thing as we have seen in this, that more the number of electron withdrawing group, more will be the delta value. We will call that proton as the de-shielded. Another thing is that now there is only one atom Br which is withdrawing electrons. But this particular, now we are talking about chemical shift of hydrogen which is directly attached to Br, hydrogen which is beta with respect to Br, and CH2 which is gamma with respect to Br. Let's say we have this molecule. All CH2s will be different. They will appear as a different peak. Their chemical shift will be different because their electronic cloud around this proton is different. CH2 which is directly attached to Br will be highly de-shielded because you know that inductive effect as I go away from this Br, as I go away from donating or withdrawing group, the impact of inductive effect will decrease, right? It is distance dependent. As the distance increases, the inductive effect will also decrease. So what you find that among these three CH2s, a CH2 which is gamma with respect to Br is the farthest. The delta value is 1.25. CH2 which is beta with respect to this Br, the value is 1.697. And the CH2 which is directly attached to Br, the value is 3.3. Which is most de-shielded? The one which is attached to Br, alpha with respect to Br. And as I go away from Br, you'll find that the delta value goes on decreasing. So see, it's the beauty of NMR. The delta value will help us to understand the location, the type of electron cloud, whether shielded or de-shielded, a lot of information about the structure we are going to get by using this NMR spectra. Rather, chemical shift will help us to understand electron cloud and obviously to draw the perfect structure. It's not about perfect structure, but it also obviously is going to help you the to tell the properties of the matter. Okay, what kind of where the substitution will take place, how the substitution will take place. So if I carry out substitution reaction in this molecule, obviously this reaction center is more reactive as compared to this and this. So indirectly I'm getting chemical reactivity. Understand chemical reactivity of that particular carbon or hydrogen by understanding the NMR spectra chemical shift of that. Now, we don't have only one factor which will affect the chemical shift. We also have, along with inductive, we have resonance. Now, see, uh, any molecule when I take, we can have all these factors affecting, or we may have only one of the factor affecting them. For example, if I talk about resonance, resonance is, we are talking about pi electrons. We are talking about conjugation. We are talking about a electron donating and withdrawing with respect to pi electron cloud. Whereas inductive is with respect to sigma electron cloud. Resonance will have always more impact as compared to inductive, that you know. And along with that, substitution, as I told you, whether it is primary, whether it is secondary proton, whether it is tertiary proton, if substitution goes on increasing, the delta value will also increase. All these three factors are because of the surrounding of that proton in the present in that molecule. That impacts the chemical shift of that proton, and because chemical shift is affected because of these properties present in that molecule, we can distinguish, we can identify different types of protons. But along with this, there is one more factor that is called magnetic anisotropy. What is anisotropy? What is magnetic? You understand. We are talking about magnetic field. Anisotropy means your molecule is divided into two unequal parts. Aniso means not equal. Isotropic, equal. Anisotropic, not equal, not same. Something which is not same, okay? Anisotropic. Now what you find that whenever we take this molecule, as we were discussing, that as the percentage of S character of sp hybridized carbon is greater, electron withdrawing capacity of sp hybrid carbon is greater, proton attached to the sp carbon should be more de-shielded as compared to sp2 and sp3. But in real sense, when practically we observe, we see that this is not happening. What you'll find that sp2 protons attached to sp2 carbon are more de-shielded, maybe olefinic, maybe aromatic, as compared to alkyne protons. Why this is so? So the answer for this is not about the electronic environment due to the bonding present in that molecule. The answer is magnetic anisotropy. Now, whenever I place molecule in the magnetic, external magnetic field, you know, they are going to align themselves. Align in such a way that your, what, the, as you know that your proton is spinning around it, it generates its magnetic field, and when it is placed in the applied magnetic field, two things can happen. One, the magnetic field of that proton will be in the same direction of applied magnetic field, or it will be in the opposite direction of the applied magnetic field. If your applied magnetic field and the magnetic spinning, or the direction of the magnetic field of your proton are in the same direction, what you'll find that the delta value is greater than expected. And if they are in opposite direction, the delta value is less than expected. This effect is called as anisotropic effect. Now, whenever we put a molecule in the magnetic field, external magnetic field, it aligns itself in such a manner that its own magnetic field is divided into two, where direction is either in the same direction of applied magnetic field or the opposite direction of the applied magnetic. What you'll find, alkyne protons fall into the region where the two directions, applied magnetic field direction and the magnetic field of your hydrogen, they are going in opposite direction, and therefore the delta value, what was expected, is much less than expected because of the magnetic anisotropy. And due to, and what you'll find that aromatic protons, olefinic protons, their hydrogens fall in such a way, they orient in such a way that they fall into a region where the direction of applied magnetic field and direction of the magnetic field of those protons, They are in the same direction. If they are in same direction, delta value is more than expected. They are in opposite direction, delta value is less. In all alkynes, what happens? Molecule orients vertically, and that is why they fall into the shielding zone of the magnetic anisotropy, and the shielding zone decreases the delta value than expected. And in case of olefins or aromatic system, which are flat, trigonal planar flat molecule, their protons fall into the de-shielding zone of anisotropy, and because of that, the delta value is greater than expected. So anisotropy means your magnetic field of the molecule is divided into two parts. One is the shielding zone, another is called de-shielding zone. If your proton fall into shielding zone, the delta value is less than expected. If your proton fall into de-shielding zone, your delta value of proton is greater than expected. There is de-shielding zone at the peripheral side, shielding zone at the central side. Your olefinic and aromatic protons fall into the peripheral side, whereas alkyne proton come in the central zone, shielding zone, and therefore the delta value is less than expected. So, next time, whenever you will talk about chemical shift, if you are talking about hybridization, the chemical shift, what observed and what is expected, they do not match. This is because three factors are because of the chemical environment of that proton. Which three factors? Resonance, inductive, and substitution. But the fourth factor is because of the instrument. The fourth factor is because of the alignment of the molecule in the instrument. If the alignment is such that your proton is coming in the shielding zone, delta value will decrease. And if proton is going in de-shielding zone, the delta value will be more than expected. So we call this effect as magnetic anisotropic effect. What is the anisotropy? We divide zone into two parts, shielding and de-shielding. If proton comes in shielding zone, delta value is less than expected. If comes into de-shielding zone, delta value is more than expected. So why? Alkyne protons are acidic in nature, but their delta value is less than aromatic or olefinic protons. Any proton is acidic means what? Can be released as H plus. Why it can be released as H plus? Because you have a sp carbon which is highly electronegative, can withstand with the electrons and give a hydrogen in the form of H plus. When you carry out any chemical reaction, acetyl proton can be lost as H plus. Acetyls, alkynes, protons are acidic in nature. We don't call them as acid, but acidic in nature means can be released as H plus. But olefinic proton cannot be released as H plus because that much electron withdrawing capacity is not there with sp2 carbon. But when I go in instrument, I see opposite thing. Why? Because of magnetic anisotropic effect. Shielding zone, de-shielding zone. Proton coming in shielding zone, delta value less than expected. Proton coming in de-shielding zone, delta value is greater than expected. So this is how the fourth factor we will talk when we talk about NMR spectroscopy. That is magnetic anisotropic effect. See here, there is a nucleus and there is a nucleus with electron density. Obviously, the isolated proton will have different spinning or different resonating uh, energy as compared to when your nucleus is surrounded by electrons. And then on the basis of that, it is good that this has impact on its absorption energy or its resonance energy. That is why we can distinguish between various protons by using NMR. So this I want to show you that this is the direction of applied magnetic field. Okay, V0 is the applied magnetic field. Let's say this is the aromatic molecule, simple benzene. Now benzene orient in such a way that see This central part you see, now you can see this dotted line. Is it visible to you? What you will find that this pink line which is shown, it is showing the direction of magnetic field of your molecule, and this is the direction of applied magnetic field. In central zone, what you will find that it is going in downward direction, and the peripheral side it is going in upward direction. The direction of applied magnetic field and the peripheral side are same, but the direction of applied magnetic field and the central field they are in opposite direction. Because over here there is opposite direction, we call this zone as a shielding zone, and the peripheral side is called as a de-shielding zone. Whenever applied magnetic field and the magnetic field of your proton or your molecule they match in the same direction, we call that as a de-shielding zone. Your hydrogen is fall in the de-shielding zone, and that is why delta value is very high. From 6.5 to 8 is the range of aromatic protons. But the moment you will find that if hydrogen is coming over here in this region, hope you must have studied about anilines. Okay, in anilines, what you'll find some protons are highly de-shielded and some protons are highly shielded. You know, in aniline molecule, you'll find that those central protons are coming in the shielding zone, whereas peripheral side we have resonating protons. And what you'll find that the delta value of the peripheral aniline protons is very high and the central is very less. So anilines, these protons were distinguished by using NMR because they fall in different zones. All are equivalent, but zones are different. That is why when I put in NMR, I can distinguish between those which are inside, directed inside, going in the shielding zone, and those who are going to the peripheral side. So this is called magnetic anisotropy, which is the fourth factor which decides the chemical shift of proton. Now, here we have a general chemical shifts. You know, silanes, as I told you, that tetramethylsilane, if I take uh, its value is not zero. We take it as zero because we want to stop somewhere and then compare with respect to that where other hydrogens are falling. Therefore, we consider it as a zero, and then from there, where my other hydrogens are falling, that will decide the chemical shift of our organic protons. So what you'll find that as I go away from the zero, I'll call it as a low filled proton, and close to zero are called high filled protons. 1, 2, 3, generally sp3 carbon protons will be there. Again, 2 to 3 sp carbon protons will be there. And from 4.5 onward to 12, all sp2 type of protons will be there. Various types of sp2 protons are there. We spoke just now about olefinic and aromatic, but as you know, that carboxylic acid or aldehydes, in aldehydes, what is this proton is attached to sp2 carbon, but it is attached to oxygen, and we know oxygen is highly electron withdrawing. So I can distinguish between CHO with respect to aromatic protons or olefinic protons, highly de-shielded because of presence of this carbon. Then if I have COOH, carboxylic acid, here hydrogen is directly attached to oxygen, highly de-shielded, it will come around 12, sometimes 13, 14 also, depending upon what structure it is, what kind of acid it is. Phenolic OH will come after 6, 7, you'll find that highly de-shielded those protons because it's acidic in nature, can be donated as H+, means it is highly de-shielded. So this is how the roughly distribution of protons you'll see in EMR, and this will help, delta value will help to understand what kind of proton is present in that organic molecule. So obviously we are going towards structure. You want to find out the structure of that molecule. Why you want to find the structure? Because once I get the structure, I can talk about its chemical properties. If it is olefinic, we'll say it will undergo addition reaction. If it is aromatic, we'll say it can go under substitution reaction. So all other chemical properties I want to find out, structure will help me to understand the chemical properties also of that particular molecule. So getting correct structure is our motto by using NMR. So for example, there is one simple spectra kept in front of you. Just now we spoke about only two things. One, how many peaks are there, and what is the chemical shift of that proton. Okay. So for example, here we have let's say all are not equivalent, but right now we consider as equivalent. All are aromatic protons, and this is aliphatic proton. Here hydrogens are attached to sp3 carbon. All other protons which are attached to aromatic ring, sp2 carbon. So in toluene, we have two peaks, one for sp3 proton, another for aromatic protons. Now you can see here it's a broad peak, it's not a simple sharp peak. You know why? Because chemical shift of these two protons will be same. These two protons will also be same. This will be different. Three protons will be very close in their chemical shift but not same. So there is clustering because one is 7.1, other is 7.2, then someone is again 7.25, something like that. They're so close that we find there's a broadening of the peak will be observed because the chemical shifts of these protons is very close. CH3, no doubt its inductive effect is there, but impact is very less. That is why it does not much withdraw or donate electrons to benzene ring, and therefore all will appear around 7.2. Benzene appears at 7.25, so this proton will also be very close to 7.2, and they will appear as one peak, and methyl will appear as another peak. So this is how we'll look at the PMR spectra to understand the type of proton. Chemical shift is helping me 7. This is 2 point around 2.4 or so. So this is aliphatic carbon proton, and this is more than 7, 7.2, 7.3. So we can understand that these are aromatic protons. So I can distinguish between these two type of proton by using my PMR spectra. But this is not over, because at the first thing, at the beginning, we had said that what we are going to look at. We are going to look at the how many peaks are there. So that will help me to understand the type of hydrogen atoms. Then I will see the chemical shift, which will again help me to understand the protons, various types of protons. The third thing we are going to see is the integration. That is relative intensity of the peak, each signal or a peak, and that will tell me how many types of same hydrogens are present in that molecule. So third information I'm going to look at is the integration of that particular peak, which will help me to get that how many hydrogen of same type are present. For example, if I take this tertiary butyl bromide, what I'll find that all these three CH3s, that is 9 protons, are equivalent in all respect. I'll see only one peak, equivalent to how many? 9 hydrogen atoms. Okay. Then if I take another molecule, let's say CH3, CH2Br, we have two types of protons. I'll see two peaks in PMR. Now we have one CH3, another is CH2. The peak height of CH3 will be greater than CH2. The ratio between the peaks heights will be 3:2. Okay, because we have equivalent protons of A type 3 and B type 2. Integration intensity of 3 hydrogen peak will be greater than 2 hydrogen. And this is how we can distinguish between CH3 and CH2 because the peak heights will not be same. Then I take another molecule. Now this particular 2-bromobutane. What you'll find that all protons are non-equivalent. There is no symmetry in this molecule. So 1, 2, 3, and 4 peaks will be observed. Now all 4 peaks will not have same chemical shift because we know the chemical environment is not same. Br alpha with respect to CH, beta with respect to this CH3, beta with respect to CH2, gamma with respect to this CH3. All 4 will have different chemical shift. Roughly, if we want to talk about, Br is directly attached to CH and highly substituted. Therefore, this is a tertiary proton will have highest chemical shift. Then among these two, this is CH3, this is CH2, both beta with respect to Br, but CH2 is more substituted. It is secondary proton. Therefore, delta value of CH2 will be greater than this CH3. This CH3 and this CH3 I compare. This CH3 is beta with respect to Br. This CH3 is gamma with respect to Br. So obviously, this CH3 will be more de-shielded as compared to this CH3, or delta value of this CH3 will be greater than this CH3. So first highest value of chemical shift will be for CH, then CH2, then CH3, B type CH3, and then A types of CH3. Why? Now you know it, right? So we'll see four things. Now the intensity. So intensity is decided by how many equivalent protons are present of that type. So here we have one hydrogen, here two hydrogen, three hydrogen, three hydrogen. So intensity of A and B will be same, height will be same, but it will be much greater as compared to C and D because number of equivalent protons for C and D are very less. So if this is 1, this is will double of this, and this is 3 times more than the peak for D. So 1 is to 2 is to 3 will be the ratio, integration ratio among these three, 4 protons. Whereas intensity of A and B will be same because number of equivalent protons. Now, how can I distinguish between two CH3s? If height is same, but their delta value is not same. So I can distinguish between this CH3 and this CH3. So now peak height also gives me a lot of information about the organic molecule. The height of the peak integration helped me to understand how many equivalent protons of this or same type of protons are present in that molecule. For example, in this molecule, we have two CH3s which are equivalent. The integration of 6 hydrogen height, 1 hydrogen, the ratio of 2 peaks will be 1 is to 6. The A proton peak will be 6 times greater as compared to B type of proton in this molecule. So like this, if I have this molecule ABC, 3 protons, 3 types of proton, 3 peaks, ABC peaks will be there. The integration will be 3 hydrogen, 2 hydrogen. So B and C will have equal heights, but B and C will not have same chemical shift. Your C is alpha with respect to Br, your B is beta with respect to Br. The chemical environment of C and B is not same. Delta value will not be same. They will appear as different peaks. So this is how we can distinguish, different protons by delta and as well as by integration. Here we have integration again, 4 hydrogens of aromatic type, 3 hydrogen CH3, 3 hydrogen, and CH2, 2 hydrogen. So we'll have 3 peaks. Again here, actually all protons are not equivalent of aromatic region. But the groups which are attached, they do not have much impact on their electron donating or withdrawing. That is why they will have very close chemical shift. And if their chemical shift is close, it will be like a cluster. And that is why we'll not be able to distinguish much about these 4 protons. Therefore, we are writing that they will appear as a same peak. So this is how the peak will look like. So this is how the spectra looks like. Okay. So height of the peak. See now in exam many times students ask that how to calculate the integration. So this is the spectra. This scale indicates x-axis, indicates the delta value. It's very blurred, not that good quality. So please excuse me. But for the timing, just try to understand. If my 0 is over here, this is my 1, this is my 2, 3, 4, 5, 6, 7, 8. So we have aromatic protons. See here, it's a broadening of the peak because all 4 hydrogen atoms were not equivalent, but their chemical shift was very close. There is clustering of the peak, and that is why I am not able to distinguish between these 4 protons will appear as a single broad peak. Then we have CH3 and we have CH2, 3 hydrogen and 2 hydrogens. So what you'll find that this is the integration, 1 is to 2 is to 1. Then this is there and this integration is there. What you have to do? That measure the distance between these two lines, measure the distance between these two lines, and measure the distance between these two lines. Add all these distances. Let's say this is x, this is y, and this is z. Add x, y, z, all distance by using a good scale. You can always measure the distance between these two lines. This line you can extend, this line you can extend and add this distance. You can extend these two lines and add the distance between these two lines. And same thing you will do here. Or add all these distances x, y, z and divide by total number of protons. How many total protons are there? So 3 of CH3, 2 of CH2, 5 and 4 of your aromatic. So 5 plus 4, 9 protons. Divide that distance. Let's say they have added distance it as a 24 mm, 32 ABC is 24, 16 and 32. The distance is 24 mm of the first peak. Second one is 16 mm and third one is 32 mm. So the ratio between them is 1.5 is to 1 is to 2. But otherwise, what we do, add 24 plus 16 plus 32. Whatever addition you get, divide by 9. It will tell you one hydrogen is equal to how many mm, and then by using that we can find out the equivalent protons present for that particular peak. So this is how integration part is done in NMR. So this is simple way for the integration. Now, if you take for your molecule or your PhD students, always remember that whenever you are supposed to find PMR, first thing what you have to see the purity of your molecule. Your compound has to be highly pure, otherwise you will not get uh, proper elucidation of the spectra. So first thing, purify your compound properly. Second thing, see the good solubility of your compound. Which solvent it is soluble, properly soluble. So polarity will help you. Most of the times you are preparing all molecules which are known, right? If it is unknown, you know the molecular weight, you know the structure. So you can always find out polarity to a certain extent and on the basis of that decide what solvent to be used. Obviously deuterated solvent you will use and then take PMR of that particular compound. Once you get PMR, you are supposed to do most of the times manually all this. You will not get all this done by instrument, okay? So if you get the spectra, first thing, see how many types of hydrogen were present in your molecule and those many peaks are there or not. If you have extra peak, you have impurity in your molecule, first thing. Then try to detect solvent peak if you have. Remove solvent peak from there and then check whether your types of hydrogen and number of peaks are matching or not. Second thing, you try to get the integration. Total number of hydrogen present in your molecule and total number of then peaks integration you will do. If it is not matching, again there is a problem in your PMR. So you have to take PMR if you are doing organic synthesis or anything, any research related to organic molecules. So your compound should be highly pure. Again, you have to do column and all that and purify it. Second thing, your integration should match to the total number of hydrogen present in your molecule. And then third thing, you'll see chemical shift, whether it is as per the structure what you have provided and the chemical shift, they are matching or not. So these things all PhD students will have to do whenever they will go ahead with their research. So a very simple molecule I have kept here. As I had discussed that if I take cyclohexane and take the spectra at room temperature, I'll get only one peak because I cannot distinguish between axial and equatorial. At low temperature, if I stop the flipping of chair, then I can distinguish between axial and equatorial. The difference is of about 0.5 ppm. The value difference of chemical shift between axial and equatorial, you'll find it as a 0.5 delta ppm is there. But here we see a single peak. Then all 12 hydrogen equivalent, you'll find that they are coming at around 1.5, 1.6 in this. These are also aliphatic protons. These are also aliphatic protons. They are at high field region of the your PMR. Here we have two types of protons, aromatic protons and aliphatic protons. See here, we are aliphatic protons, we have 6 hydrogen equivalent, whereas aromatic we have 4 hydrogen equivalent. Peak height you can see the ratio is 3:2. This is 3 times, whereas this is 2 times later, what you will find that chemical shift, the aliphatic 2 point, now this is 2.2 delta ppm with d-shielded proton because it is directly attached to aromatic toluene like in paraxylene. And this is aromatic. CH3 do not have much impact donating withdrawing, little it is donating only. So around 7 you will find all aromatic protons coming, 4 hydrogen. All are equivalent, so they will come as a, see here, this is a sharp singlet over here for aromatic protons. Why? Because these all 4 protons are equivalent. Previously we had seen, what you find, the previous spectra, here clustering was there. Because all 4 protons are not equivalent. Here, these 4 protons are not equivalent, and that is why what we see is a clustering, or you can see a broadening of the peak. But the moment you see the other spectra here, a singlet just like your methyl proton, very sharp peak is observed because all protons are equivalent in all respects. So this is the third information we are looking at is the integration, which tell you about the equivalent protons of the same type. Now the fourth most important, which will give you exact details about the structure of the molecule, is splitting pattern. What is splitting? Splitting means what we were expecting, that a smooth line will be there as a signal. Just now we have seen such a nice smooth line we have seen here. But the previous spectra, there was something, there was no smooth line, you know. See here, there is splitting, there is splitting, there is splitting. Why the splitting is taking place? So the answer for the splitting of spectra is called as coupling of protons. What is coupling? Couple means what? Two. Two protons, they interact with each other. And that interaction is recorded in the form of splitting of lines.
मॅडम एक मिनिट इंटरप्ट करू.
Yes.
3 वाजेला एक पुढचं जनरल आरएमचं लेक्चर आहे.
ओके.
मी तुम्हाला रिक्वेस्ट करतो की उद्या कंटिन्यू करणार का तुम्ही?
उद्या काय वार आहे? शुक्रवार. I'll continue tomorrow. I don't have a supervision. Yes.
Okay. Thank you, madam.
3 वाजता थांबूया आपण.
हो 3.
Okay. So, splitting a pattern is nothing but what a line is splitted into several lines. These several lines, not just like that. There is some rule, there is some pattern to be followed, and which is decided by again the structure around that proton. So that is decided by certain things. Okay. So again, splitting will help me to understand details of the surrounding of that proton. So this surrounding of proton can be exactly found out from the splitting pattern. So this splitting is decided by various factors like two protons, how close they are. What is the distance between these two protons? Are they neighboring protons? Since the distance between these two protons is of 3 bond, whether it's 4 bond or more than 4 bond. What is the dihedral angle between these two protons? And what type of groups donating, withdrawing present around them? All these 3 factors will decide what kind of splitting will take place and how it will look like, the spectra will look like. So today we will not discuss about the splitting pattern. Tomorrow, as sir said, we'll talk about the splitting pattern tomorrow, how it is decided by the distance between various protons and the dihedral angle. So we have seen 3 factors today. Hope you have understood. If you have any doubts what we have done right now,
Thank you very much, ma'am. We truly appreciate the way you explained the fundamentals of NMR instrumentation, active nuclei,
the timing
concept
and
of
everything
proton
will
splitting and
be
deshielding.
told by Vishnu sir.
All the research scholars are invited
Accordingly, we will do tomorrow
to ask their
about the
question.
splitting pattern, the fourth factor which decides, which gives information about the structure of the molecule. So today we'll stop. And in case you have any question, tomorrow we'll discuss about it. Okay? Okay, sir, shall we stop?
Yes, ma'am.
So thank you, students. Thank you for being there. Hope you have enjoyed the lecture. Thank you so much.
Thank you, madam.
Participants are requested to join the next session of research methodology using the link of research methodology. Thank you, ma'am.